As we move into discussing how to find solutions to higher order ordinary differential equations or systems of ordinary differential equations, it's going to be really important to access our linear algebra knowledge. And in fact, it turns out that the sets of solutions to ordinary differential equations, also known as the solution spaces, are in fact themselves vector spaces. So remember your vector spaces from linear algebra days. We are going to be making use of lots of linear algebra theory. How does this linear algebra theory help us? Say, for example, we have an ordinary differential equation, and we've got two solutions to that differential equation, y1 and y2. Would it be the case that if we took their sum, the sum could also be a solution? That answer depends on what kind of differential equation it is. And in fact, this claim says that if your differential equation has this particular form, ay double prime plus by prime plus cy equals 0, then it is in fact the case that any linear combination of two solutions to that differential equation will also be a solution. What are the key features of this differential equation? Remember, here's where our categorization comes in handy. The key important features are that it is linear and homogeneous. All right, how do we prove this claim? If we want to show that any linear combination of two solutions you give me is also a solution, then what we're going to have to do is take that linear combination, which we are naming function y, and simply plug it back into the ordinary differential equation and verify. So we take y, we take its first derivative, and we take its second derivative. I suggest you pause the video and give it a try yourself and see if you can verify that y as a linear combination of y1 and y2 is also going to be a solution to this general linear homogeneous second order ordinary differential equation. Okay, so the first thing we do is simply plug the solution in. So we've got coefficient A in front of y double prime, which we read from here, plus coefficient B times y prime, which we read from this calculation, plus coefficient C times y. So in summary, we have taken our three computations for y prime, and y double prime, and plugged them in to the ordinary differential equation where they belong. Now let's rearrange. And what we get is C1 times all the terms that have y1, y1 prime, and y1 double prime, plus C2 and all the terms involving y2, y2 prime, and y2 double prime. What do we now notice? If you look at each of these sums, as we said, y1 and y2 are already solutions to the ordinary differential equation. So when you plug them in, since the ordinary differential equation is homogeneous, those sums end up being 0. We have therefore shown that y solves the ODE. What are the key linear algebra ideas we are using here? We are using the ideas of linearity, linear combinations, and homogeneity. We also are going to need the concepts of linear independence, linear operators, and vector spaces. In fact, we can define a linear operator that represents differentiation. If you recall from your linear algebra days, every linear operator has a matrix multiplication representation, and every matrix multiplication can be represented by a linear operation. In the same way, every differential operation can be represented by a linear operator. Now we can actually define a linear operator to represent our differential equation, and we know that L is linear precisely when the operator applied to a linear combination of two objects is equal to a linear combination of the operator on each object individually. This concept of thinking about the differential operator as a linear operator may be helpful as you bring your linear algebra knowledge to bear on looking at solution spaces. Notice that in homework 3, problem 6, you solved a linear algebra problem that described the set of solutions to ax equals b when the right-hand side b was not 0. In other words, not homogeneous. In homework 4, problem 6, you are going to show that what we claim above, in other words, that the linear combination of two solutions to our ordinary differential equation is also a solution, that claim is not going to apply if we lose homogeneity. Let's go to the next page and remind ourselves of what a vector space is. Here I have provided you with an excerpt from the textbook Linear Algebra with Applications. And what we have here is the set of requirements for a space V to be a vector space. Remember that the set V, together with the operations of addition and scalar multiplication, is a vector space if the following axioms are satisfied. These axioms are all arithmetic axioms. And recall that a vector space needs the following qualities: commutativity, associativity, an additive identity, which we usually call 0, an additive inverse, which we usually identify by putting a minus sign in front, the ability to distribute, and a multiplicative identity, which we usually call 1. In addition to these arithmetic axioms, we also require closure under these arithmetic operations. So if we have an element from our vector space X, and you take a scalar, then the scalar times X is still included in the vector space. Similarly, if you add two elements from a vector space together, then you want that sum to still be in the vector space.
There are important consequences when we start taking a linear algebraic perspective, and we view the operation of differentiation as a linear operator, and we view the solution set as a vector space.
In particular, the set of all solutions to a second-order, linear, undriven, homogeneous differential equation is a vector space, as we've been saying. The set of all solutions to an nth-order, linear, undriven, homogeneous differential equation is also a vector space. So in other words, we can now generalize easily from second order to higher order. And finally, because these solution spaces are vector spaces, we inherit the ability to talk about basis functions that are linearly independent solutions and that span the space of solutions. So two additional important concepts from linear algebra that you'll want to refamiliarize yourself with will be the concepts of a basis and span. These will allow us to prove that the set of all solutions to an nth order linear undriven differential equation is going to be an n-dimensional vector space. And that is how we can know that we have found all the solutions to the differential equation that we have, drawing on our linear algebra theory. Let's go to the next page and test ourselves on the concept of basis. Pause the video here and answer these questions for yourself, whether these sets of vectors are a basis for the real plane, R2. Hopefully you found that each one of these statements is true. Why? Because each one of these sets of vectors is a linearly independent set.
And of course, they are not just linearly independent, but as a set, they form a span of all of R2. How do we know that? Because we remember from our linear algebra days that in order to form a basis for an n-dimensional space, we need exactly n linearly independent vectors.
Remember from homework 1, problem 1, we were asked to verify that these two solutions, y1 is e to the minus t and y2 is sinh t, both satisfied this second order differential equation, which as you can see is linear and homogeneous. Now the question is y, which is a linear combination of those two solutions, also a solution? Why or why not? We now know from our theory the following. Let's first note that the hyperbolic sine and the hyperbolic cosine are both linear combinations of the functions e to the x and e to the minus x. And by the way, e to the x and e to the minus x are linearly independent functions. As to the question about whether y is also a solution to the differential equation,
what do you think the answer is, and can you explain why? Take a second, pause the video, and make sure you have the answer clear in your own mind.
The answer is yes, because we are taking a linear combination of two solutions that satisfy a linear homogeneous ODE. More specifically, let's take a look at what the basis for our solution space might be. Suppose the basis for our solution space is
e to the t and e to the minus t.
Suppose then we also represent e to the minus t by the vector 0, 1 and e to the t by the vector 1, 0. Then the hyperbolic sign is represented by 1/2 minus 1/2, since the hyperbolic sign is a linear combination of 1/2 e to the x minus 1/2 e to the minus x. Since e to the x and e to the minus x are linearly independent, we also have the fact that 0, 1 and 1/2 minus 1/2 are linearly independent basis vectors for the real plane. These basis vectors are linearly independent, and as solutions to the ODE, all linear combinations are also going to be solutions to the ODE. Here's a bonus concept for those of you who might be interested in how we can transition between a linear operator and a matrix representation. So suppose our representation of e to the x is the vector 1, 0. When we take the derivative of e to the x, then the differential operator should send the vector 1, 0 to 1, 0. Similarly, when we take the derivative of e to the minus x, the differential operator should take the vector 0, 1 to 0, minus 1. So what is that differential operator in matrix form? It turns out that d equals 1, 0, 0, minus 1 is the matrix representation for the linear operator that simply takes the first derivative of the function that you plug in. Okay, that's it. When we see each other in class, we will start working on modeling systems that lead to the second order ordinary differential equations that we have been discussing. Take care. Bye.